A warm greetings, dear viewers. I am Dr.S.Saranya, Assistant Professor, PG and Research Department of Chemistry, Seethalakshmi Ramaswamy College, Tiruchirappalli. In this module, I am going to discuss about Introduction to Organometallic Chemistry. Organometallic chemistry is a fascinating field which was a latecomer into the subject field of chemistry. People realized it as a subdiscipline only in late 1950s. This field has grown at a phenomenal pace during the past few decades due to its potential and significant applications. At the end of this module, you will understand the definition of organometallic compounds, how the organic ligands are classified based on its hapticity, then how the classification of organometallic compounds are made, then you will know about 18 electron rule and the various exceptions to 18 electron rule, and you will know about the methods to count the electrons, and finally the applications of organometallic complexes. Organometallic chemistry acts as a bridge between organic and inorganic chemistry. The first organometallic compound of the transition metal was sea salt. Naturally occurring organometallic molecule is very rare. Vitamin B12, that is cobalamin, is one of a few naturally occurring organometallic molecule. Now let's look into the definition of organometallic compounds. The compounds containing at least one direct metal-carbon bond are called as organometallic compounds. And the branch of chemistry that deals with such compounds is called organometallic chemistry. Here, the term metal in this definition includes all those elements which are less electronegative than carbon. We all know that the electronegativity of carbon is 2.5. The metals and metalloids such as silicon, boron, arsenic, germanium having lower electronegativities are bonded directly to the carbon atom. Compound should possess at least one direct bond between a metal and carbon of organic molecule. Here, the term metal includes the elements of periodic table such as main group elements, transition elements, lanthanides or actinides. On the other hand, the organic molecules of various classes of compounds includes alkane, alkene, alkyne and aromatic ligands. The bond between metal and carbon may be ionic, covalent, or in the case of aromatic ligands, it can either bonded through a sigma bond or pi bond. There are some exceptions to the organometallic compounds where the metal-carbon bond is present. Traditional inorganic chemicals such as sodium cyanide, even though they have a metal-carbon bond, they are not classified as organometallic compounds. Similarly, metallic compounds of alkoxide, pyridine, triphenyl phosphine, dialkyl ether, dialkyl sulfide, carbonates, organic amines, organic acids, for example sodium acetate, are not considered as organic compound, since the carbon atom in these compounds is not directly bonded with the metal atom. Compounds of carbides and graphite intercalation are excluded from the family of organometallic compounds since the carbon is not from the organic moiety. The next concept which I am going to discuss is hapticity. Hapticity is nothing but the number of atoms in a ligand attached to the metal atom. So it is denoted by the prefix, the Greek letter eta, followed by a superscript indicating the number of ligand atoms attached to the metal atom. Here you can find an example of cyclopentadiene anion ligand where it can coordinate to a metal through 1, 3 or 5 carbon atoms. So you can see the first example where only one carbon is attached to the metal atom. So in the second example, 3 carbon atoms are attached to the metal atom. So in the last example, all the 5 carbon atoms of the cyclopentadiene anion ligand is attached to the metal atom. Therefore, it may act as a mono, tri or pentahaptoligand. Organic ligands are classified based on its hapticity as eta 1 monohaptoligands, eta 2 dihaptoligands, eta 3 trihaptoligands, eta 4 tetrahaptoligands, eta 5 pentahaptoligands, eta 6 hexahaptoligands, eta 7 heptahaptoligands, and eta 8 octahaptoligands. Eta 1 monohaptoligands are a type of ligands where it is attached to the metal atom through only one carbon atom. The examples of these type of ligands include simple alkyl, carbonyl, carbene, carbene, and allyl ligands. Here you can find the examples of various monohaptoligands. Eta 2 dihaptoligands or the organic ligands where it is bonded to the metal through only 2 carbon atoms. Its example includes alkene, alkyne, where the bond corresponds to the 2 carbon atoms of double or triple bond. The next one is the examples for the trihaptoligands where 3 carbon atoms are attached to the metal ion. Here are the examples for the trihaptoligands. Tetrahapticity are exhibited by the organic molecules such as butadiene or cyclooctadiene, norbornadiene, where 4 carbon atoms are attached to the metal ion. The next is the pentahaptoligands. An example of pentahaptoligand is cyclopentadiene anion ligand where it can coordinate to a metal ion in several ways. Here the ligand is bonded to the metal through 1, 3 and 5 carbon atoms. The cyclopentadiene anion ligand can also behave as a monohapto, trihapto or pentahapto in a single organometallic compound. So here in this titanium complex, you can find that the cyclopentadienyl rings on the left hand side is attached to the metal through all the 5 carbon atoms. On the other hand, the cyclopentadienyl rings are attached to the metal through only 1 carbon atoms from each ring. So, this example indicates that a cyclopentadienyl ring act as a monohapto as well as pentahapto ligands. So here you can see the next example, that is a tungsten complex where the cyclopentadienyl ring acts as a monohapto as well as trihapto ligands. Further, the ligands which can change its hapticity is called as functional ligands. The next example is the eta 6 hexahaptoligands where 6 carbon atoms are attached to the metal atom. Similarly, the next is the eta 7 heptahaptoligands where 7 carbon atoms are attached to the metal atom, and the last one is the eta 8 octahaptoligands where 8 carbon atoms are attached to the metal atom. The next concept is the classification of organometallic compounds. On the basis of the periodic table, organometallic compounds are classified into 3 types. The first classification is main group organometallic compounds. And the second classification is transition metal organometallic compounds. And the third classification is lanthanide or actinide organometallic compounds. So now let's look into the first classification, that is the main group organometallic compounds. The main group organometallic compounds are typically considered to be those of the S block, that is the group 1 and 2 elements, and the heavier elements of the P block, that is the group 13 to 15 elements of the periodic table. So there are several examples for this main group organometallic compound. Some of the important examples are Grignard reagent, triethyl aluminium, sodium cyclopentadienide, N-butyl lithium, etc. The next classification is the transition metal organometallic compounds. So these are all the compounds of D block elements. The examples of these compounds are Gilman's reagents, Coleman reagent, Wilkinson's catalyst, etc. So here you can find an example of tetracarbonyl nickel complex where the carbonyl ligand is present. So carbonyl, we all know that it is a typical inorganic molecule, but it is considered as organometallic compound because its properties are very similar to the other organometallic compounds. So the last classification is the lanthanide or actinide organometallic compounds. So these are all the compounds of the inner transition elements. So the example for this is uranosin. The next concept is the 18 electron rule. 18 electron rule is a very important concept that is to be discussed in organometallic chemistry. So 18 electron rule is nothing but the sum of the valential electrons of the transition metal or metal ion and the electrons donated by the ligands is equal to 18. So this 18 electron rule provides a closed and stable valential configuration of n-1 d10 ns2 np6, that is, this gives a count of 18 electrons. The complexes which obey 18 electron rule are considered to be stable. Valence electron count in organometallic complexes can be calculated using two different methods. The first method is the oxidation state or ionic method, and the second method is the neutral ligand or covalent method. By counting the number of valence electron, one can predict the stability of the complex, presence of metal-metal bonds, presence of terminal or bridging ligands. According to the first method, that is the oxidation state or ionic method, in order to calculate the total valence electron, it is necessary to take in account of the charge on each ligand and to determine the formal oxidation state of the metal. The next is the neutral atom method. According to this method, each metal atom and the ligand is treated as neutral. If the complex is charged, then appropriate number of electrons are either added or subtracted to the total. For example, if the complex has a negative charge, then we have to add the appropriate number of electrons to the total. Similarly, if the complex is positive charge, then we have to subtract the number of electrons to the total. So here is an example for the total valence electron count using oxidation state or ionic method and neutral atom method. So according to oxidation state or ionic method, we have to consider the formal oxidation state as well as the charges on the each ligand. So manganese plus, it contributes 6 electrons. The next is the carbonyl ligand where each carbonyl contributes 2 electrons. So totally there are 5 carbonyl ligands. So 5 into 2 gives 10 electrons. And each hydride ligands, it gives 2 electrons. So totally 18 electrons. Similarly, the neutral atom method will also give the same result, but here the metal as well as the ligands are considered neutral. So metal, it contributes 7 electrons, that is outer electronic configuration of manganese is 3d5 4s2, so totally 7 electrons. So each carbonyl ligand, it contributes 2 electrons, so there are 5 carbonyl ligands, so 5 into 2 gives 10 electrons and each H, it gives 1 electron, so totally there are 18 electrons. So both the oxidation state as well as the neutral atom method gives the same result. So one can follow any of the following methods to calculate the total valence electron. The table shown here helps us to know the number of electrons contributed by each ligand in both oxidation state as well as the neutral atom method. Electrons that is contributed by each ligands. So various types of ligands are given here. An important class of organometallic compounds follow a 16 electron rather than 18 electron rule because one of the 9 orbitals is very high in energy and usually vacant. These complexes with 16 electrons are common for square planar complexes of Da transition metals. The examples for this 16 electron complexes are Wilkinson's catalyst, Vaska's catalyst, and sea salt. The 16 electron complexes can often be just as stable or even more stable than 18 electron complexes of the same metal. So there are many complexes which do not follow 18 or 16 electron rule, but they are even stable. Now let's look into the important applications of organometallic compounds. The various applications includes homogeneous catalyst, example Vaska's catalyst, Wilkinson's catalyst, etc. It is used as synthetic reagents, for example Grignard reagent, Gilman's reagents, etc. It is used for the synthesis of organic compounds as catalyst. The next is it is used as a therapeutic agents in pharmaceutical industries. Organometallic compounds are used for the manufacturing of semiconductors. It is also used for the protection of light emitting diodes or LEDs. It is important to know that so far 8 Nobel Prizes have been awarded for the research work on organometallic chemistry. Even though the discovery of this chemistry was so late, its significant properties and applications made this field grow in a phenomenal way. Dear viewers, I hope that this module has bring up a reaction and catalyzed you to study more about organometallic chemistry. Thank you for your patience.